programmers and hackers. The user just wants boring software to make boring spreadsheets to get boring stuff done at work. But in their naivety, users often get penetrated by hackers with high levels of riz, who employ social engineering to steal personal data, intimate photos, and crypto wallets. But then you've got programmers. They're the unsung heroes who make all the software in the world work, but they too get penetrated by hackers. If a programmer leaves the backdoor open to their mainframe, it could lead to catastrophic consequences that cost them their job and their employer billions of dollars. The lesson to be learned here is that you want to be the one doing the penetrating, not some stranger in a foreign country who doesn't even care about your feelings. In today's video, you'll learn the fundamentals of ethical hacking and pen testing by looking at 10 free and open source tools that you can use right now, all of which are available by default on Kali Linux, a distro optimized for ethical hacking. By the end of this video, you'll be a legit wannabe hacker who can take down entire nations, but if you like to do bad things, you need to turn this video off right now. The tools in this video, if used non-consensually, it could break many international laws that land you in prison. So never do penetration testing on a website or network without permission. But now that all the bad guys have clicked off this video, let's learn how to use some of the most powerful and dangerous hacking tools. To follow along, I would highly recommend installing Kali Linux, and the desktop version is awesome. Although Microsofties can install it via WSL, or if you don't want to use Kali, you can just install each one of these hacking tools individually. But the best way to get started is to spin up your own virtual private server on Hostinger, the sponsor of today's video. Their platform gives you the power and flexibility to run anything you want without locking you into a complicated and expensive cloud platform. You can run a basic Linux server like Arch with powerful hardware like NVMe SSD storage and AMD EPYC chips. You can easily manage containers with a Docker VPS and their free Docker manager, or self-host entire by password, and now our hacking journey begins. The first tool you need to know about is Nmap. It's like the peeping Tom in your neighborhood who looks through all the windows in your house without actually breaking in. On a network, like the one you're connected to right now to watch this video, there's likely multiple hosts connected to it, like your computer, your PlayStation, and your smart lock, and the purpose of Nmap is to map out a network. It does this by sending packets over an IP range, it then analyzes their responses to figure out which ports are open, which operating systems they use, to help you find backdoors to exploit. Like if grandpa misconfigured something on his network, you can hack his printer to send him a message. To use it, simply use the nmap command, followed by an IP address you have access to, like your local network, or even a URL that you have permission to penetrate. If we do that on a website, you'll notice we get the IP address back, and it found that ports 80 and 443 were open. That's pretty cool, but we can also do a more aggressive scan with the A option. This will not only scan the network, but also try to detect the operating systems, and we'll use something called tracer route to track the path of the packets across the entire network, which can help detect misconfigurations that we can exploit. If you're interested in packets though, another tool you'll need to know about is Wireshark. It's like that guy at a party who tries to eavesdrop on every conversation. It allows you to inspect what's happening on the network at a microscopic level. You'll want to use the GUI on this one because it collects tons of data from hundreds of different protocols, which are all captured in real time and can be analyzed offline. For example, if you record the traffic on your network right now and notice all this weird traffic going to an IP address in North Korea, you can inspect the actual payload and might find out that they have access to those photos that were intended for only you and your future ex-wife to see. And now you might be radicalized and ready to fight back. Metasploit is perhaps the most powerful hacking framework out there. It's like a Swiss Army knife with an AK-47 attached to it that allows even the most unskilled script kiddie to launch an attack. For example, we might be able to gain access to a Windows machine with a reverse shell, thanks to the Eternal Blue vulnerability. Open up the Metasploit console and search for Eternal Blue. That should bring up a list of potential Windows targets. We know that Grandpa is still on Windows 7, so let's go ahead and use that exploit. From there we can set a payload to use a reverse shell, and configure the local host to our own IP address. And then finally run the exploit command. Congratulations, you just made a successful penetration. You can now access all the files on this computer, change the desktop background, and install even more malware. But Metasploit is almost too powerful, and if you use it, you'll miss out on a lot of cybersecurity learning opportunities. The next tool you need to know about.
Okay, I'll stop it there. And for this week, we'll be learning some neural networks. So we'll be working with MNIST Classifier. And I put the link in the chat for the GitHub. And let's watch a quick video on neural networks so that you guys can understand it more. And then we'll dive into the code.
Here are 5 things to know about neural networks in under 5 minutes. Number one, neural networks are composed of node layers. There is an input node layer, there is a hidden layer, and there is an output layer. And these neural networks reflect the behavior of the human brain, allowing computer programs to recognize patterns and solve common problems in the fields of AI and deep learning. In fact, we should be describing this as an artificial neural network, or an ANN, to distinguish it from the very unartificial neural network that's operating in our heads. Now, think of each node or artificial neuron as its own linear regression model. That's number two. Linear regression is a mathematical model that's used to predict future events. The weights of the connections between the nodes determines how much influence each input has on the output. So each node is composed of input data, weights, a bias or a threshold, and then an output. Now, data is passed from one layer in the neural network to the next in what is known as a feed-forward network. Number three. To illustrate this, let's consider what a single node in our neural network might look like to decide, should we go surfing? The decision to go or not is our predicted outcome, or known as our y-hat. Let's assume there are three factors influencing our decision. The wave's good, 1 for yes or 0 for no. The waves are pumping, so x1 equals 1 for yes. Is the lineup empty? Well, unfortunately not, so that gets a 0. And then let's consider, is it shark-free out there? That's x3. And yeah, no shark attacks have been reported. Now, to each decision, we assign a weight based on its importance on a scale of 0 to 5. So let's say that the waves, we're going to score that one. Yeah, no, this is important. Let's give it a 5. And for the crowds, that's W2. Not so important. We'll give that a 2. And sharks, well, we'll give that a score of a 4. Now, we can plug in these values into the formula to get the desired output. So y-hat equals 1 times 5 plus 0 times 2 plus 1 times 4, then minus 3, that's our threshold, and that gives us a value of 6. 6 is greater than 0, so the output of this node is 1. We're going surfing. And if we adjust the weights of the threshold, we can achieve different outcomes. Number 4. Well, yes, but number 4, neural networks rely on training data to learn and improve their accuracy over time. We leverage supervised learning or labeled data sets to train the algorithm. As we train the model, we'll want to evaluate its accuracy using something called a cost function. Ultimately, the goal is to minimize our cost function to ensure the correctness of fit for any given observation. And that happens as the model adjusts its weights and biases to fit the training data set through what's known as gradient descent, allowing the model to determine the direction to take to reduce errors, or more specifically, minimize the cost function. And then finally, number 5, there are multiple types of neural networks beyond the feed-forward neural network that we've described here. For example, there are convolutional neural networks, known as CNNs, which have a unique architecture that's well suited for identifying patterns like image recognition. And there are recurrent neural networks, or RNNs, which are identified by their feedback loops, and RNNs are primarily leveraged using time series data to make predictions about future events like sales forecasting. So, 5 things in 5 minutes.
Okay. So basically, well, neural networks as well as, all this AI talk, it's not really AI, it's more of a statistical prediction. So even like ChatGPT or Gemini, all it does really is it gets input from the user and tries to build out the solution using just probabilities of what word comes next the most often based on the training data that they worked on, right? So whenever we train data, we're really just training these neural networks or all these things, algorithms, to just get these weights. And we use these weights to basically predict what comes next. So today we'll work on the MNIST classifier. So we'll basically have, let me share my screen. So we'll basically have like data. Like, where do I put? Yeah, I think it's these. So we'll have training data that will feed into the classifier, which will train on it using the neural network, and it will basically build a model. And this model will be this one, which is .pt, which is PyTorch. And we'll use this trained model to basically, let's hide this, to pass in our image and use those weights to determine if what number it is. And let me, okay, I think new people came in, so here's the link to this week's GitHub, which you guys can look at. And here's the VS Code Live share, where we'll do our coding in. Okay. And I think we start with Nicholas this week. Yeah. Nicholas, can you share your screen whenever you're ready? And I'm pretty sure I enabled sharing. And there's two files. One is the MNIST classifier template. That's basically where we'll train the model. And we have the main template, which is where we'll have the code to pass in our image and use the model to predict which image it is. Oh, let me accept you. You should have it now. Okay. Should be line. I think it's the second function. Go down, build model. I think we were in the middle of building our model. Yeah. So we have the two layers. So this is where we are building our layers, as you saw in the video. Okay. So we have ReLU. So after ReLU, we'll start with in the same, yeah. Enter. We'll do nn dot max nn dot max pool 2D. Yep. And in it's a function, so yep. And in the argument, it will be kernel size equals 2. Okay, let me move it down. Yep. And then next layer we'll have nn dot conv2d,
Hmm?
conv2d. Yep. And we'll have in channels equals 16. Out channels equals 32. Kernel size equals 3. and padding equals 1. Yep. And then next layer, the final layer, actually, second final, relu in place equals true. Put the in place equals true. Actually, I don't even think you really need to. Yeah, equals true. And then next layer we'll have nn dot max pull to the max pull to the with kernel size 2. Yep. So basically, we're really building out this layers, right? Of how you saw in the video as well, how there's input layers, I mean, input nodes and output nodes. And basically, max pull to the is basically, you guys can think of it as a summarizer. So its main job is to really reduce the height and the width of your data. So it doesn't really have an impact on your in and out channels. And next, conv2d, that's basically like a extractor. So it looks for like patterns or similar things in your data. And then relu is basically like a activator, which really just introduces some. It basically allows your neural network to like learn the complex patterns. And basically through this, we're really building out this neural network where we pass in the data and we get some output, some weights. Next, we'll have, after the features, we'll have, so outside of the sequential, yeah, enter, we'll have self.classifier equals nn dot sequential, and in the arguments we'll have nn dot flatten, and it's a function. Yep. And then we'll also have nn dot linear,
Do we put
as
anything
part of the
inside
argument
it?
beside it. So do comma after flatten. Yeah.
We're not gonna have anything inside, I guess.
Yeah. No arguments for this flatten. Linear. Yeah, I think you have double L. And in the linear, we'll have arguments. So we'll do in features equals 32 times 7 times 7.
Mhm.
Multiply by 49. Yep. And out features equals 128. Yep. And we'll also have nn.relu in place equals true. Yep. And next, we'll also finally have nn.linear with in features equals 128. and out features equals 10. And that's it for the classifier. So after the classifier, backspace, we'll have another function called forward in the tiny CNN model. Forward, so WARD. Yeah. And remember for classes method, we do self, and we want to add argument as well called x. So comma x. Yeah. And in the function, we'll do x equals self.features. And it's a function, and we pass in x. Features is a function. No, self.features and then the bracket. X. No, you don't return in the function argument. Yeah, enter. X equals self.classifier, and we pass in x. Yeah, and then return x. Yep, enter. Backspace, backspace. Yep, and then return tiny CNN. So instance. And yeah, CNN bracket. Yep. So that's the instance of the class.
Do we put anything inside the bracket?
No. Uh, the reason is basically we're trying to return an instance of the tiny CNN. So if you see, it's actually aligned with the class. So it's basically outside of the class. So we're basically just building the class and returning it inside this build model function. And a way to make an instance of a class is to call it like a function. But for these, we don't pass in anything because although it says nn.module, that basically is like inheritance. So that's your parent class. So the tiny CNN's parent class is nn.module, while define underscore underscore init is basically your arguments for the class, but it has none. So yeah, you don't pass in anything. But yeah, you can stop sharing now. Okay. That was basically it for really building the model, which is crazy, but yeah. And then we'll basically set up the data loaders now. So basically passing the data onto the neural network. And we'll go with, yeah, I think since this should we do, okay, I think we can do Adam next. Adam, can you share your screen when we're ready?
Mm.
And we'll go Albert after Adam. So just be ready, Albert. And while we wait, just for class logistics, I believe today's the last class of fall semester, and we have 2 weeks off, and then start a spring semester on March 3rd and 10th, and then spring break for 3 weeks. So today's the last class for the fall semester, just so you guys know. And yeah, data loaders. Delete the not implemented there. So basically, we'll build the data loaders, which is basically the data that we pass to the neural network. Uh, so below the doc string, nope. Oh, nope. Weird. Albert, can you try again? Maybe I left the screen too long. Wait, who is this? Is this Caden? I'm not even sure. Okay, okay. If you want Caden, you can go as well. I think Adam's still trying to bring it up. It's okay.
I'm ready to share.
Okay, you can share it. Okay. Hmm. Okay, you'll have to go down a bit more to right after this function. So get data loaders right there. Delete the arrays not implemented there. Yeah. So we'll do transform equals transforms.compose. And like it says, we'll pass in a list of transforms.toTensor and transforms.normalize. Tensor is OR. Yeah. And it's a function. Yeah. And transforms.normalize. And we'll pass in mean equals, or you don't even have to put mean equals, you can just do 0.13. Yeah, up to you. Yep, and standard deviation. STD is standard deviation. Equals 0.3081. Equals 0.3081. Yep. And then we do train dataset after these lines. Enter. Train underscore dataset equals torch vision dot datasets. So this is where we load the data data sets. Yeah. And we pass in datasets dot MNIST.
Passing what?
So datasets dot. Uh, no, I meant like torch vision dot datasets dot. Yeah. Dot MNIST. Yeah. And then we pass in root equals the location of where the data is, which is, you won't have it on Replit, but yeah, equals, and then string dot slash data. String, comma, train equals true, download equals true, and transform equals transform. And for those wondering what MNIST is, it's basically stands for Modified National Institute of Standards and Technology. Basically, they just hold a whole bunch of data sets for handwritten pixel images of handwritten digits. So we're basically fetching data from MNIST. And we'll do test data. So tab, tab, and test data, test data set equals torch vision dot. And then you can just copy from above and just set train equals false. It'll be the same thing. Yep. And then we'll now load it. So enter tab, train loader, equals data loader. And we pass in train data set that we defined. We're going to set the batch size to the batch size, which is in the argument of this function, where I set it to 64. And shuffle equals true. And we're also going to set num underscore workers, so the number of workers. Num underscore workers equals 2. Workers equals 2, and comma. Pin underscore memory equals true. And for the next one is the test loader. Now you can, yeah, that's part of the whole function. For the test loader, it will be the same except shuffle equals false. Enter. And we'll return the train loader and the test loader. So when you're training neural networks or any type of data, I mean, model, AI model, you'll need data sets and you'll need to set it up into 3 partitions. One will be training data, so what your AI model will train on. And then after it trains, it will like to test itself. So you'll have test data. And then you'll have actual data where we send it and it should generate some prediction as to what it is, or like in this case, what handwriting digit it is. And you want to pass in the test loader. Yeah. And yeah, that's it. You can stop sharing now. And I will copy what you just did to the template. Okay. Next, we'll do one training epoch. So next, I think, Albert, can you share your screen? One training epoch basically is, well, you guys know iterations is the same as epoch. So it's basically saying in one iteration of training the model, what happens, and we'll code what happens. Oh yeah, it says in the comments, run a single training epoch or inter or session. Delete the arrays not implemented error. And we'll do model.toDevice. And then we'll do model.train. So this is basically, we're setting up the arguments for how we would like to train the model. And then running loss or total loss up to you equals 0, 0, 0.0. And we'll set total batches to 0. Underscore batches equals 0. And for each image and targets, so for images and targets, uh, no each. For each like image and target. So images, call it targets in loader. So here we're basically using the data loaders, right, that we just set. Okay. In loader, we have images. Okay. We're basically setting up how we're training the model. So you have the images set up, target set up, and we're basically setting up our parameters. So our gradient, which is it's an equation for getting the weights. Then we have the forward pass, and we're computing the loss function. Backpropagation is basically where we pass data backwards. So we recursively go back and update our weights. And here we're updating the parameters, and we're adding to the loss function. And adding to total batches, which is how many iterations we've done. Enter, subtract, backspace. We're going to calculate the average loss. Okay, I think it's keep on falling. Okay. Average loss equals, yep, total divided by total batches. Yeah. And then you want to return it. Yeah, that's basically it. Thank you. You can stop sharing now. Next, we'll do the evaluation. So, Kaden, can you share your screen? Okay, I think here. Okay, your thing is really zoomed in. Maybe go like one more minimizer. Or is this comfy for you? Or up to you. Yeah, delete raise not implemented error. So here we're trying to compute the classification accuracy. So how accurate our model is compared, I mean, using the loaders, data loaders. So we'll do model dot to device. So we're setting up the parameters. We also do model dot eval. So setting up for evaluation mode. And we'll do correct equals 0, total equals 0. So we're basically gonna see how much we got correct versus how much we didn't get correct. Total equals 0, yeah. With torch, with enter. With torch dot no gradient or no grad. Colon for images and targets in the loader. For images, targets in the loader, images equals images dot t to device. Enter targets equals targets dot to device. And outputs equals model of images. So we're passing the model the images and getting an output. And do underscore comma predicted. We don't really care about the first value here. Equals torch.max of the outputs and dimension equals 1 or dim. Outputs, just outputs, comma 1. Yeah, outputs is wrong. I think you have the extra A. Yep. And next we'll do add to the correct. So correct plus equals predicted equals targets dot sum dot item. Yep. So if the predicted answers are equal to the targets, then we'll add them up. Dot sum dot item. Enter total plus equals targets dot size of 0. Yep. Enter backspace accuracy. Return correct divided by total. If total is greater than 0, or else just return 0. So we're basically returning back how accurate our model is currently as a float between 0 and 1. And yeah, that's it for this function. Next, we'll have the run training, which you can stop sharing now, and we'll do Adam one, Talbert one, Kino one. Charlie, let me share screen. Oh, yeah. Here, I think that's better. Okay. Yeah. Is it going up on its own or? Okay. No, we'll just do it. So run training, we'll basically do the full training routine. So getting it from the start and training it using the train one epoch. So we'll loop through that. So raise not implemented error will delete that. So let's do device equals get device. So this is where and tab so that you're in the function. Device equals get device. So this is where we choose our GPU or CPU. Most of you won't have a GPU, so automatically select your CPU. Enter, and usually you can print it saying this is your device, but we don't need to do that. Let's build the model. So model equals build model. And model dot to, okay, I think okay, model to model dot to TO. Model dot TO. Oh, TO, TO. Yeah, TO. Yeah. Device. So bracket device. Yep. And next we'll load the data. So train loader and test underscore loader, train underscore loader, test underscore loader equals get data loaders. And we pass in batch size, which we set at the top of run training arguments, which says 64. And we're doing 5 epochs or iterations. You don't need to put 64, you can just put batch size. Batch. Yep. Now let's initialize the loss and optimizer. So enter, yep. Criterion, so CRIT. CRIT equals NN dot cross entropy loss. So cross, yeah. Enter optimizer equals optim dot atom, and we pass in model dot parameters, which is a function, comma LR equals LR, which is also defined at the top. It's 0.001. Enter. We'll do the training loop now. So for each epoch, so for epoch in range of 1, comma, epoch plus 1, colon, yeah, average loss equals train 1 epoch, and we pass in the model, the test loader, train loader. Since we're training it now, comma, criterion, which is crit, comma, optimizer, comma, device. And ACC equals evaluate. So we're getting the accuracy. And we pass in the model, test loader, and the device. And oh yeah, whenever you guys train models, after each iteration, it is pretty good to like print it out of the current status of the AI training. So let's print it out. So print f string, so f, yeah, epoch, and we'll do curly bracket, epoch after that, yeah. And division symbol. So we're finished these many epochs out of this much epochs. So just do it outside of the division symbol outside of the, yeah. And we'll do curly bracket again. And then we'll do epoch s, epochs. Yep. So it's basically telling the user how many epochs we've gone through and how much is left. We'll also want to print the loss function. Do print. Yeah, f string, and we'll do loss colon equal or colon average loss. And let's just keep it at the enter. And we'll also want to print the accuracy. So accuracy, yeah. Yep, and we pass in ACC times 100. Since it's percentage. Yep, and next, enter outside of the for loop. We'll do torch.save. So this way we're saving the model, right? We don't have to run the training model every single time. Save, and we'll do model dots in the save argument. Model dot state underscore dict. Yep. And it's a function. Comma checkpoint path. Checkpoint underscore path. Yep. Enter. But yeah, enter torch dot. Final evaluation. So we'll do final ACC. So final accuracy equals evaluate, and then we do evaluation again using the model, the test loader, and the device. And yeah, you can stop sharing them. Okay, so that's it for the classifier. So let's see. Okay. Okay. So now let's see if this runs. Oh, I did not check path equals. We'll have some name MNIST CNN.pt. So this is basically going to be our file for the checkpoint. So where we save our model. And let's actually. Okay. Let's just check everything works. There's no errors that we see. So our lint is not showing any errors. Do you guys know what lint is, right? ESLint or linters. Linters are basically what shows us these errors. So let's say these epoch is not defined, etc. Those are all done by the linters. MNIST, let's delete this. Actually, let's just name a different one. Let's rename it to in class MNIST, and we'll run this. Here is training, and we have error in place. Okay, it says run training. In place equals true. Got an unexpected argument in place. That's weird. Did I have this right argument? Okay. I have no idea why this error is appearing. Oh, maybe let's do this using 3. Maybe this will work. Weird. Okay. I'll let you guys know after I debug this later on. But assuming it works, you guys will get some file like this. And with this is basically the AI trained model. So with this, you guys really can't do anything, right? So now we'll build the main.template, main_template file, where we basically pass in image and it will process it using this MNIST CNN PT file, so PyTorch file with the model, and we'll basically run an inference using the model. And this is basically how most AI solutions work. Like the place I used to work at, Motorola, we used to have security systems based on AI models, so the users can basically run AI inferences on footages of people, and all the AI models would be trained beforehand and passed on to products or installed on products. Anyways, next person will work on pre-process image. So whenever you guys work with AI models or especially images, you guys will need to have this process of processing this image so that it's in the right format so that the AI model was trained on, or so that it'll be easier for us to pass that image into our AI model. So that's what we'll do. Next, James, can you share your screen, or Ian, maybe? Up to you. James, are you able to share your screen? You can try it. Okay. Doing another work, disinfect. That's fine. Okay. So yeah, pre-processed image, they'll be not implemented there. Delete the arrays not implemented there. Yeah, enter, and yeah. So let's do image equals and capital I image dot open the image path. So for this file, we'll pass in an image location, so it'll be a string. And in this function, it says preprocessed image, and part of the argument is the image path. So yeah, you pass in the image path, and we convert it. So dot convert outside of the function. So dot open dot convert. Yeah, and it'll be a string, capital L. String, capital L. Yep. So this basically just grayscales it, so just black and white. Enter, yeah. Image equals image dot resize. So we're really tweaking the images so that it fits to the model. Resize, circle bracket again. Once open bracket. Yeah. 28, comma 28. Outside of the first, yeah. Yeah. Image dot capital I image. Comma first. Dot bilinear, all caps. BI, all caps. BILINE. Yeah. Enter. And we'll do transform equals T, capital T dot compose. Capital T, just capital T. Dot compose. And we pass in a list. And in that list, we have T, capital T dot to tensor. No string. Dot to tensor. Yep. And that'll be an empty function, so no arguments. Comma. Capital T dot normalize. And we pass in the same mean and standard deviation as the training models. So we pass in the tuple. So you need a circle bracket again and do 0.1307. Outside of, yeah, keep it like that. Comma. Outside of the next circle bracket, yeah. And then do comma. And then circle bracket. And 0.3081. And that's it. So it should be 30.1. So like that. That should be good. Enter. Tensor equals transform image, pass in the image to the transform function. Dot unsqueeze. Yep, that's dot unsqueeze. Then we pass in 0. So this is basically the dimensions. So enter and then return the tensor. So now we're done pre-processing the image. Now let's go on to predicting it. So you can stop sharing. Ian, if you want to have a go at it, the next function will be really easy. So if you want, you can try it. So Ian, can you share your screen and we'll try out the next function, which is predict image. Okay. If not, then we'll just start from the beginning again. So Nicholas, can you share your screen? It'll be really quick, this one. So the main template.py. Go to the second tab. Yeah. Go down to the next function, predict image. Delete arrays not implemented there. Okay, now we'll call the preprocess. So tensor equals preprocess image. Preprocess image, which is the function before. So preprocess image. Uh, yeah, that one. And no dot at the front. Yep. And we pass in the image path, image underscore path, which is the first argument of the function, and enter. Uh, next line, enter. Yeah. Model.eval. So we'll put the model in evaluation mode, and that's a function, so circle bracket. Yep. And we'll do a forward pass, so tensor dot enter. And model, you spelled model wrong. It's you have an extra E. Yep. Tensor dot tensor equals tensor. Sorry, tensor equals tensor. Yes. Tensor equals tensor dot TO TO. So two. TO T. T as in tensor. Yeah. Two. So no T at the end. Yeah. And it's a function, and we pass in device. Enter. Yep. And then we do with WITH. Torch dot torch dot no underscore grad, which is no gradient. And that's a function. Colon. Uh yeah. Enter log IT S equals model, and we pass in the tensor. Model is a function, and we pass in tensor. Enter, and we do predictions or pred, so PRED equals logits, so LOGITS dot argmax no S. And we pass in DIM as in dimensions equals 1.
Hmm?
DIM as in dimensions equals 1. Yeah. And we do dot item after the function though. Like attached to the closing circle bracket. So we do logits dot argmax dot no in the line before. Yeah. Item, which is a function. Yeah. And then we return the prediction, which is pred. Enter. Yeah. Return pred. PRED. Yep, that's it. So basically, we're making the inference. We're passing it the model. We're pre-processing the model. We're setting up the model for evaluation. We're passing the model our tensor, which is that image or that preprocessed image, and we're basically getting out this prediction. Now this is our inference, and you can stop sharing. Okay. Next, okay, we'll just finish what we can. So next is the main function. Does anyone want to do this? Want to try and go ahead and try and implement this function? If not, we'll go to Adam. Adam, can you share your screen?
Hey.
Thank you. Weird. I'm having some connection issues. Okay, you'll want to go down to refresh. Do you have the main underscore template?
Where?
It's a separate file.
Oh,
So you'll want to go here and
no.
select main underscore template.
Where?
I sent it in the GitHub. It should be in GitHub.
Oh,
And the link is in the chat. Actually, before that. Okay, I think I got the error. Let's try this now.
And share now.
Okay. Go down to the last function. Main. Yep. And delete. Weird. I'm getting network issues. Anyways, yep. Delete the array is not implemented there. Okay. I'm gonna stop the collaboration session because I'm getting some network issues. But yeah. Okay. Now let's set up the parser. So when you're working with Python, you can set up parse arguments for functions. So when you call this file, not on Replit, but on your computer, you can execute the file using parser and set up some arguments. So let's do parser equals argparse dot argument parser. And we're going to set the description as, yeah, sure, that's good. MNIST digit classifier. Yep. And do enter parser dot add argument image path. And it's a type of string. And to help the user, it's just a path to an image file that we're passing in to run the inference on. Yep, help equals path to image file. And we'll do path parser dot add argument. And we'll do dash dash ckpt works, or you can do model or yeah, comma, type a string, and this will be the file path to our PT file or the AI model. PT as in PyTorch equals MNIST underscore CNN dot PT CNN dot PT comma help equals path to model checkpoint. Enter args equals parser dot parseargs. Now, parser is, or argparse is really used, especially for scripting. So in the real world, you guys will use parser if you guys are scripting on servers or appliances, etc. Okay, I think that's it for today. You can stop sharing now. Yep, thank you. Okay. Now I will share my screen. I believe. We'll just finish this once we come back, and let's do a booklet on neural networks. Transform. Okay. Link is in the chat, and I will stop the recording